The sweetest compound known is the molecule Lugduname, but it has never seen commercialization, and it seems there was no effort made to do so. It was discovered and patented by the University of Claude Bernard in Lyon, France in 1987, who let the patent expire in 1994 after they stopped paying maintenance fees. Lugduname is also not available as a research chemical, so it can't be bought anywhere. All this also means there is no data on its safety in humans, though some related compounds in this family of molecules have been tested in pigs and it seems to be safe. Besides, the researchers had to have tasted it to determine the potency, and it would only take a very small amount to sweeten something, so it is difficult to even ingest a toxic amount. Lugduname is said to have a potency of 220 to 300 K. The potency of a sweetener is measured against regular sugar, also known as sucrose. So sucrose always has a potency of 1. The way potency is determined is by dissolving a known amount of the sweetener in water and diluting the concentration up to the point it has the same sweetness as a sugar solution of which the concentration is also known. So if you, for example, need 0.1 gram of sweetener per liter of water to get the same sweetness as a 50 gram per liter sucrose solution, then it means the sweetener has a potency of 500. Since Lugduname has probably only been tasted by researchers, the potency is given as 220 to 300 K, because different patents report a different value. And because it is based on human taste, it will generally have some margin of error, and it could also be personal, since taste and smell have genetic components that affect your experience. This makes me very curious about what it is like in pure form. Does my tongue even have enough receptors to perceive the sweetness of pure Lugduname? Will it completely overload my taste buds and become unpleasant? Or is it absolutely amazing to experience such a sweetness explosion? We're gonna have to find out. To make Lugduname will require a fair bit of work, and it took me many months to get it right. Since there is no easy to copy method for it online, I had to rely on my skill. So I tried a bunch of different routes to see what would work, and in the end, I of course got it to work. Otherwise this video wouldn't be here. So this is the whole reaction scheme to get to Lugduname as its hydrochloride salt. To do so, I first need to make its precursors, which are this methylene dioxybenzylamine and this isothiocyanate. These are not commercially available, so I have to produce them from chemicals that are the most similar to these precursors and are available in good quantities for a fair price. So I can start from the corresponding amine to make the isothiocyanate, and for the methylene dioxybenzylamine, I can start from O-vanillin, or skip a step and start from 2,3-dihydroxybenzaldehyde for a higher price. I tried both, and when I have the precursors ready, I can start building the Lugduname molecule with several steps. So the first thing I will make is the methylene dioxybenzylamine that I need in the end. Since it takes the most steps, I first need to know if it works before I make the other precursor, which is most likely to succeed anyway. I will start the synthesis from cheaply available O-vanillin. So for that, I set up a large flask in a heating mantle and add in a mixture of 600 ml of glacial acetic acid and 180 ml of 48% hydrobromic acid. As you can see, this is quite a harsh mixture, since methyl ethers are, as far as I'm aware, one of the most difficult ethers to cleave, so we need to kind of nuke it. So now I add 150 grams of O-vanillin directly into it and allow it to dissolve. While it's dissolving, I degas the liquid by blowing nitrogen through it for about 30 minutes. This process will knock out the dissolved gases from the atmosphere, among which is oxygen that can lower the yield, and replace it fully with inert nitrogen. When that's done, I close it off for a second to limit contact with the air, and I then prepare the condenser on which I fitted an adapter with a balloon filled with nitrogen. When I open the valve, nitrogen starts to force its way through the condenser and flush out the air. When the balloon is almost empty, I attach it to the flask. The reaction setup is now air-free, and I can run the reaction. So I start the water flow through the condenser and heat the mixture to a boil for at least 9 hours. In this reaction, we have a typical acid cleavage of an ether to an alcohol. In this case, a methyl ether is one of, if not the most difficult type of common ethers to cleave, as it generally requires harsh reagents or conditions, which is usually not so nice for the other groups that are on the molecule as well, which is reflected in the yield. How the reaction proceeds is quite simple. First, the ether is protonated by the hydrobromic acid, followed by attack of the bromide ion onto the methyl group, moving the carbon-oxygen bond electrons onto the oxygen, balancing its charge and leaving behind methyl bromide with the final product. When I come back, the mixture is black because these conditions also generate a lot of tar, but it should be finished. So I immediately swap out the condenser for a short path distillation apparatus and distill off a large portion of the solvent. After that, I neutralize the remaining acid with sodium bicarbonate. This step is important since the presence of acid during the next step will destroy a lot of the material. I add more water to allow the bicarbonate and acid to react, and I shake it to loosen the material. I added bicarbonate until it stopped bubbling from the addition, and I stirred it strongly. The solution was pretty much neutral at this point, so I distilled off all of the water, leaving behind tar that contains the product which partially sublimes on the walls of the setup. I now heat the mixture to over 200 C under a very strong vacuum to distill over the product. A short path is not so good for this, as it plugs quickly and doesn't allow for proper heating of the condensing part to get down the solid. So what is inside I washed out later, and I changed the setup to a regular vacuum distillation setup but with a tube instead of a condenser. I then distill it over with the aid of a heat gun. If it gets too hot in the condensing part, I wrap it in some wet towels, though most of it solidifies in the setup and I have to melt it with the heat gun to make it move down to the flask. After a while, no more product distills over and it should be finished. I washed this setup out with the solvent toluene, as well as the previous short bath, as to get it all together in some toluene, which is also needed for purification. So to purify it, I need to recrystallize it. For that, I will boil the toluene and get it all to dissolve. When it is all dissolved in the boiling toluene, I transfer it to a larger flask and set it up for short path vacuum distillation to reduce the volume of toluene. After that, I can add an excess of the solvent carbon tetrachloride, in which the product is very poorly soluble. So when cooled, it will cause all of it to crystallize out. There's probably a good alternative to carbon tetrachloride. It's just what the literature used here. Anyway, I moved the flask to a freezer and left it at minus 25 C, and it caused all of the products to crystallize out. Now to get it out, I set it up for vacuum filtration. I wet the filter with carbon tetrachloride and then filter all the material through. After crushing and drying the material, it became a dry, pure yellow powder with a woody aromatic smell. In the end, the yield of this run was 56.8 grams, which is 41%, so that's pretty decent compared to the literature. When I tried this reaction before, I did not neutralize with sodium bicarbonate, giving a yield of only 9%, so we see why that step is important. Anyhow, I've used both materials with success in the next step, but when I filmed the next reaction, I used the commercial material. I also noted no difference in yield between commercial and self-made product, even though mine looks a lot better. So for the second step, I set up a flask in a heating mantle and add in 200 ml of dimethylformamide as a solvent. Then as the first reactant, 25 grams of 2,3-dihydroxybenzaldehyde, which is the whole container. As a base, I add in 27.5 grams of potassium carbonate. Then as a catalyst, I add 1.66 grams of copper 2 oxide. As the second reactant and final ingredient, I add in 15.3 ml of dibromomethane. I then do a semi-lazy way of flushing out the air with nitrogen, by first blowing nitrogen into the flask, then I attach a condenser, and on top of that, I add a balloon filled with nitrogen. When I pull up the condenser, the balloon starts blowing nitrogen through the condenser and flushes out the air. I then reattach the condenser and leave the balloon attached, keeping the setup under nitrogen while allowing any overpressure to go into the balloon. I then turn on the water flow through the condenser and start heating the mixture to a boil, and I leave it like this overnight. In this reaction, the two adjacent hydroxyl groups, often called a catechol after the molecule catechol, are transformed into a benzodioxyl using dibromomethane. The way it works is that phenols like this catechol are slightly acidic and can be deprotonated by a base like potassium carbonate to form the corresponding phenoxide ion, and the phenoxide ion is a good nucleophile. In the meantime, the copper oxide catalyst coordinates to a bromine from the dibromomethane, pulling on its electrons and increasing the bond polarity of the carbon-bromine bond. This makes the carbon more electrophilic and improves its susceptibility to being attacked by a nucleophile such as the phenoxide ion. So the phenoxide ion attacks the carbon of the dibromomethane, and the bromine takes up the carbon-bromine bond electrons to form the bromide ion, which pairs up with the remaining potassium ion to form potassium bromide. The resulting intermediate undergoes the same reactions again, but this time intramolecularly to form the final benzodioxyl product. When I come back the next day, it looks exactly the same, but it should be finished. So I take it off heat and allow it to cool down to room temperature. I then take it away and set up a filter with a glass frit, and put some sea light on top. I spread it more evenly with a spatula and pull a vacuum to pack it down. I then filter the whole mixture through, and this sea light will help to hold on to insoluble particles of the copper oxide and maybe some tar that has formed. The solution is also very stinky, because the solvent slowly decomposes to dimethylamine when refluxed. I wash out the flask and filter with approximately 400 ml of the solvent dichloromethane to make sure I get out all the product. I throw away the residue on the filter and take the filtrate, which is still black. I move all of the black filtrate to a separatory funnel and wash it with a total of 1 liter of water to remove the original DMF solvent. When that's done, I have put it all into this flask, to which I add some sodium sulfate, which will absorb any water that has come through. I now set up a new flask in the heating mantle and add a tiny funnel that I plug with some cotton. I then filter the whole black mixture through to remove the sodium sulfate and any solids that settled out during washing. After 100 years, it is done, and I set the filter up for distillation to remove all the DCM. When it stops distilling over, I put a light vacuum to make sure all the DCM is gone. I then replace the short path with an even smaller short path and pulled a very strong vacuum on the setup, while also increasing the heat. Immediately a liquid starts distilling over, which seems to be some remaining DMF that hasn't washed out. When that stops coming over, I swap out the receiving flask and increase the temperature even further, while continuing pulling a strong vacuum. I assist the distillation with heat gun, and another liquid starts coming over at 90 degrees Celsius, at a pressure of approximately 0.3 millibars. This should be the product, and it is a slightly yellow liquid. I continue the distillation until it stops coming over, and only some tar remains in the distilling flask. In the end, I am left with 16.7 grams of the product 2,3-methylene dioxybenzaldehyde as a slightly yellow liquid, which is a yield of 62%. In the literature I followed, they achieved a yield of 84%. It's still a decent yield, and I will use it directly in the next step. I first move all of the product to a large flask. This compound has a melting point close to room temperature, so part of it had to be scraped loose because it's solidified. After sitting for a while in the flask, it all became solid, and I added a stir bar on top. I then add 32 ml of ethanol, start stirring, and mix it with 158 ml of water. I let it stir for a second, and I add 9.33 grams of hydroxylamine hydrochloride as a reactant. It looks like it wasn't a huge fan of that, and it all crushed out as a solid mass. Either way, I just continue normally, and I add 14.3 grams of sodium carbonate as a base. Upon addition, it starts to react, and the solid slowly loosens again. I add some extra ethanol to wash out the funnel and also help the stuff dissolve. After a short while, it starts to stir normally again, and I leave it like this overnight. In this reaction, the aldehyde group is converted into an aldoxene, also generally called an oxime, by reacting with hydroxylamine. The first thing that happens is that hydroxylamine hydrochloride undergoes an acid-base reaction with sodium carbonate to form hydroxylamine that partakes in the following reaction. Hydroxylamine is a nucleophile that can attack an electrophile like the aldehyde group, forcing a pair of the carbonyl bond electrons onto the oxygen. The resulting intermediate undergoes a proton transfer from the nitrogen to the oxygen to balance their charges. In the following molecule, a lone electron pair from the nitrogen forms a double bond. At the same time, the hydroxyl takes up the remaining proton, and the protonated hydroxyl is kicked off as water, giving the final aldoxine product. When I return the next day, it has become yellow, and some stuff precipitated. Now to make sure all the salts are dissolved, and to precipitate out all the aldoxine product, I add a bunch of water, since oximes are generally not so water soluble. I then take it aside, and we see the white product settle to the bottom. I then filter it all through a glass frit and wash it with even more water to get rid of impurities. I let it dry on the filter for a second, then take it off the filter and scrape all the product into a crystallizing dish. In the end, I am left with 19.6 grams of the wet aldoxine product as a white powder. Since the product is still wet, I can't determine the exact yield, unless I dry it. But it doesn't have to be dry for the next step, so I won't waste my time on that. So I immediately continue with the next step, which is converting the aldoxime into an amine, which can be done by a reduction, like hydrogenation. For that, I set up a large flask in a heating mantle and drop in a stir bar. To that, I add a mixture of 300 ml of ethanol and 9 ml of concentrated hydrochloric acid. The ethanol is a solvent, while the hydrochloric acid will act to immediately turn any amine that is formed into its hydrochloride salt. I then attach a funnel and pour in all of the aldoxime I just made. I wash it down with ethanol and remove the funnel. Then as the catalyst, I add 1 gram of 10% palladium on carbon. I attach a two-way gas adapter, and on the right side I attach it to a vacuum pump. On top I put a balloon filled with nitrogen. I then cycle between opening the way to the vacuum and to the nitrogen balloon, replacing the atmosphere in the flask with nitrogen and removing all the oxygen. This is to make sure that the mixture doesn't spontaneously ignite when I add hydrogen. When that's done, I replace the nitrogen balloon with a hydrogen balloon and repeat the same steps, turning the atmosphere in the flask into a hydrogen atmosphere. When that's finished, I leave the way to the balloon open so that the reaction can continuously take hydrogen out of the balloon. I leave this to stir at 30 C until it stops consuming hydrogen. What happens in this reaction is that the aldoxime is reduced to an amine by hydrogenation. The way it works is that the catalyst, palladium on carbon, as the name suggests, has very tiny pieces of palladium loaded onto its carbon surface, seen as the white pieces in this very close-up picture of the catalyst. When the catalyst comes into contact with hydrogen, they attach themselves to the surface of the palladium pieces. This significantly lowers the energy required to allow it to react with the oxime. And so, in these mild conditions, the oxime double bond can pick up the hydrogens to form a hydroxylamine, of which the nitrogen-oxygen bond is able to pick up another pair of hydrogens in the same conditions, splitting off water and producing the final amine. Midway during the reaction, we can see that the reaction has sucked out all of the hydrogen from the balloon, so I replaced it with a new one. When it seems that it is finished, to finish it off safely, I remove the hydrogen balloon and replace it with a nitrogen balloon, and repeat the same steps as earlier, to replace the atmosphere with nitrogen, but this time to remove the hydrogen. When that's done, I can safely remove the adapter and let the mixture come into contact with the air. I then take the black mixture and set it up for vacuum filtration. In the funnel, I put a bunch of stacked filter papers, to make sure all the palladium on carbon is filtered out. Ideally, you should filter it through sea light. I wet it with some ethanol and then filter the whole mixture through normally, and I wash it out and down with more ethanol to get out all of the product. When it's done, the filter is clear. I moved all of it to a crystallizing dish to boil off all the ethanol, but boiling down this solution caused it to gradually become yellow, probably because the amine isn't a fan of getting boiled, which, I mean same, but that's a bit unfortunate. So I tried to recrystallize it from ethanol instead to make it white again, but that didn't work so well. In the end, I just decided to add a bunch of diethyl ether to the concentrated solution, causing the amine salt to precipitate out as a white solid, and the yellow stuff to remain dissolved. So to collect it, I set it up for vacuum filtration through a glass frit, and wash it with more ether. I then scrape it all off the filter and move it to a crystallizing dish. In the end, I am left with 10 grams of the amine hydrochloride salt as a white powder, which is a yield of 48% from the aldehyde, which is a little bit sad, also considering that it is definitely still wet. And a little spoiler, it is very important that it is fully dry before using it. I think the hydrogenation is just so extremely slow that it is better to perform a different type of reduction, or do it under pressure. But I did get it completely white instead of dirty brown like the literature, so that's at least a win. The NMR analysis also shows a bunch of water is present, and the rest agrees with literature, so I can be sure it is what I think it is. Now I have successfully made the first molecule that I need to make Lugduname, so I will set it aside for now and move on to the next one, which is 4-isothiocyanidobenzonitrile. This can be made from the commercially available 4-aminobenzonitrile in one step. I tried 3 different methods to make it, of which the first one was extremely bad and the second one was just bad, so I don't recommend those. Instead, go for the third one, which was the only one that worked normally, and so that is also the one that I will show. So to get started, I set up a large flask with a stir bar and add in 400 ml of chloroform as a solvent. I then attach a funnel and add in 20 grams of the starting material 4-aminobenzonitrile. This method uses a biphasic solvent system, with water as the second solvent, of which I add 150 ml. These two liquids don't mix, but can facilitate reactions at the places they contact. And some of the material will also transfer between them, and I add grams of sodium bicarbonate as a base. I then let it stir like this for 10 minutes to make sure it is sufficiently dissolved. Now the final reagent is thiophosgene, the sulfur counterpart of the very toxic gas phosgene. But thiophosgene is a liquid and not as toxic, so it is a lot easier to handle, though I still have to take it up with a syringe since it comes with a septum cap. So I take up 8 ml of thiophosgene with a syringe and we see its pretty red color. I then just gradually spray it all into the flask and it immediately turns yellow and then orange from the color. I then leave it to stir strongly for 1 hour. In this reaction, the amine from 4-aminobenzonitrile is converted into an isothiocyanate by reacting with thiophosgene, giving 4-isothiocyanidobenzonitrile. This reaction works a lot better in this biphasic solvent system, but I can't find exactly why. Either way, the reaction I did with DCM as a solvent and triethylamine as a base was a big failure. How it works is that the amine is a nucleophile that attacks the electrophilic thiophosgene carbon. This moves a pair of thiocarbonyl bond electrons onto the sulfur, and the resulting intermediate is subsequently deprotonated by the sodium bicarbonate. In the following molecule, the electron pair of the sulfur returns to reform the thiocarbonyl and kicks off the chlorine as it is a good leaving group. Then something similar happens, but this time it's a free electron pair from the nitrogen forming a nitrogen-carbon double bond, resulting in the other chlorine being kicked off. Like earlier, the remaining proton is taken up by the sodium bicarbonate, again forming water, carbon dioxide and sodium chloride. And we are then left with the final product, 4-isothiocyanidobenzonitrile. Both thiophosgene and isothiocyanates can actually react with water, but water is a relatively poor nucleophile, and the reaction is extremely slow at room temperature, which is why it isn't a problem in this reaction time. But it is important to not leave it for longer than necessary, otherwise the yield will slowly decrease as it will still react. When I come back, the color has mostly disappeared and I stop stirring. Since there's an excess of thiophosgene, it will always stay colored, and there's also a little bit of white solid that's settled out. I then move it all to a separatory funnel and take the bottom chloroform layer which contains my product. I discard the remaining precipitated solid and water layer, and I've put all the chloroform in this beaker, to which I add some sodium sulfate to absorb droplets of water and traces that dissolved in the chloroform. We see it has become less cloudy because of that. I then set up a flask in a heating mantle and attach a funnel that I plug with some cotton. I filter all the dried chloroform through to remove the sodium sulfate again. I set this filtered up for distillation to distill off all the chloroform and excess thiophosgene. When that's done, product is left behind as a yellowish solid. In literature, they triturate their product with a 1-to-1 mixture of diethyl ether and hexane, though it is not the same molecule as mine. I decided to try it and left it to stir overnight in this mixture so that all the solid is broken up. They then filter it and take the filtrate, but I just took the residue. In the end, I am left with 18.4 grams of 4-isothiocyanidobenzonitrile, which is a yield of 67%, and I'm fine with that. Now that I have all the building blocks ready, I can start building Lugduname. The first step is to make the thiourea precursor, for which I need the isothiocyanate I just made. Of that, I add 8.3 grams to a flask and then 110 ml of acetonitrile as a solvent. As a second reagent, I add 7.1 ml of commercially available glycine tert-butyl ester that I freebased myself. The reaction begins almost immediately, and it causes everything to dissolve. Within a minute, all of the product precipitates, and the stirring is no longer effective. So I just add a little bit more acetonitrile and shake it so that it can stir for a little bit longer, to make sure it has all reacted. What happened is a reaction between an amine and isothiocyanate to form the corresponding thiourea. In this case, I used acetonitrile, but dichloromethane is usually also an appropriate solvent. How it proceeds is first through nucleophilic attack of the amine onto the electron-deficient carbon of the isothiocyanate, moving one pair of thiocarbonyl bond electrons onto the sulfur. In the following intermediate, this electron pair returns to form a thiocarbonyl, moving one pair of carbon-nitrogen bond electrons onto the nitrogen, which at the same time deprotonates the nitrogen on the other side, in the end leaving us with this thiourea molecule. After about an hour, it is all reacted, and I set the mixture up for vacuum filtration. I first wet the filter with some acetonitrile and then filtered all of it through. I wash it with some ether and let it dry on the filter for a second. I move it all to this dish, and the yield turned out to be 10.4 grams of an off-white solid, which is 69% and is similar to my other runs. It is possible to evaporate down the acetonitrile and wash it with hexane and ether to get a little bit more out of it. Looking at the NMR analysis, it confirms that I have my molecule, and there is also some water present. So it is wise to dry it completely by putting it under vacuum with some mild heat, because the next reaction is sensitive to water. I dried it, but it only lost about 1% of its weight. Moving on with the next step, I set up a flask and add in 105 ml of dry dimethylformamide as a solvent. I then add in 6.1 grams of the thiourea that I dried, and also 4.3 grams of the methylene deoxybenzylamine hydrochloride I made earlier. Then to freebase this amine, and as a base for the reaction, I add in 6.3 ml of triethylamine. The reaction is a bit sensitive, so to start out, I cool it down to about 0°C in an ice bath. When it has cooled down, I add in 6.2 grams of mercury 2 chloride as a desulfurization agent. The mixture quickly turns milky and I leave it to stir in the ice bath for an hour. When I return, it has become black from precipitating mercury sulfide, which means the reaction is proceeding. I then take it out of the ice bath and leave it to stir at room temperature for a day. In literature, they mention to leave it until TLC shows the reaction is complete, but I checked and it didn't seem to go to completion, even after adding some additional mercury chloride and solvent. My theory is that the presence of some water forms the corresponding urea, which has nearly the same polarity as the thiourea. And when you look at the TLC, it seems as if the thiourea doesn't disappear, but actually it is the urea, even though the thiourea is the limiting reagent. In hindsight, it is probably best to use a stain specific for thiocarbonyls, and then you don't even have to run the plate to see if all the thiourea is gone. One such stain is 0.1% silver nitrate in methanol, which is specific for thiocarbonyls. Or if your reaction is completely free of water, then you can do it normally and stain it with something else. Anyhow, this reaction is a type of desulfurization of a thiourea to form the corresponding carbodiimide. How it proceeds is first through nucleophilic attack of the thiocarbonyl onto the mercury, kicking off a chloride ion, while a free electron pair from one of the nitrogens moves to form a double bond to make up for it. The following intermediate is deprotonated by the base triethylamine, forming triethylamine hydrochloride. The other nitrogen also moves to form a double bond, forcing the carbon-sulfur bond electrons to form a sulfur-mercury double bond, kicking off another chloride ion, giving this intermediate a mercury sulfide, which precipitates in its beta form, causing it to be black instead of the typical red from the alpha form that we are used to. The intermediate is again deprotonated by the base triethylamine, affording the final carbodiimide molecule. We then immediately have a second reaction because the methylene dioxybenzylamine has already been added. The carbodiimide that is formed is a potent electrophile and can easily be attacked by an amine to form the corresponding guanidine. So the amine attacks the carbodiimide's electron-deficient carbon, moving a pair of bond electrons onto one of the nitrogens. The charges are quickly balanced by a proton transfer, giving the guanidine product, which exists as a resonance structure, but I will keep the dis form only. The reason why everything should be dry is because the carbodiimide can also undergo nucleophilic attack from water, forming the corresponding urea, which is undesirable. After about a day, it has become even more black, and I assume the reaction is finished. Now for the workup, I first dilute it with some ethyl acetate. I then set it up for filtration to remove all the black mercury sulfide. To make sure no particles pass through, I add a layer of sealyte on the filter, and I wash it down with more ethyl acetate. I discard the filter cake, and I am left with a yellowish filtrate. I move all of it to a separatory funnel, and to take out the remaining salts and DMF, I wash it several times with water and dilute it with more ethyl acetate. It also forms a foamy precipitate, but I'm not sure what exactly it is. I expect it is trash, so I just filtered it through some cotton to get rid of it. The filtrate still contains some water and particles, so I add some sodium sulfate to absorb the water. I then just filter it again through some cotton, which gets rid of all the remaining solid. I set the filtered up for short path vacuum distillation to get rid of all the solvent, and I am then left with an orange liquid containing the product. Since it's not fully pure, I will just do column chromatography to clean it up. So I set it back in the mantle and add some dichloromethane to redissolve it. I add a little bit of sea light and boil off all the solvent again, forming an intimate mixture of sea light and the product. This will allow us to conveniently dry load the sample on top, and it generally gives better separation than wet loading. So I've set up a column and mixed 180 grams of silica gel with 500 ml of the elument, which is 5% methanol in dichloromethane. I pour it all down the column and let the elument run through it a few times to pack the silica. When that's done, I add a small layer of sand on top of the silica to protect it. Then on top of that, I add all of the sea light product mixture from before and a bit more eluent. I let the eluent run through and the components in the product easily let loose from the sea light and enter the silica where they will be separated. We can see the stuff moving through the column, and I just wait until all of the yellow stuff comes out, and then I collect all that comes after. It also seems the column decided to start cracking for no reason, but it wasn't a problem. When that is done, I move all of the collected solvent containing the desired product to a large flask and distill off all the solvent. And after that, some yellow oil is left behind. on which I pull a direct vacuum to pull out all the solvent. When that's done, I am left with a small amount of an orange oil. I suspect, and I have experienced, that these guanidines aren't very good with heat, causing them to discolor. So unfortunately it becomes orange, but it should still be good to continue. Ideally any heat should be avoided, but that's not really an option for me in this case. So for the last reaction, I dissolve the material in 40 ml of acetic acid and 20 ml of 1,4-dioxane. I then attach a septum and bubble hydrogen chloride gas through this solution, which will remove the third butyl ester. Normally the hydrogen chloride is added as a solution in 1,4-dioxane, but I didn't have that ready and this should give the same result. What happens in this reaction is a deprotection, where originally the third butyl ester was placed there because if it was an acid, it would react in the previous steps. But now all that is finished, so it can be converted into the free acid to give the active compound Lugduname as the hydrochloride salt. Without this acid functionality, it has no taste. How it proceeds is through protonation of the ester, after which the adjacent bond moves onto the oxygen to give the carboxylic acid, leaving behind the third butylate cation, which combines with the remaining chloride ion to give third butyl chloride. We are then left with Lugduname, of which the guanidine is mildly basic and can only be protonated by strong acids like hydrogen chloride, though in my experience it seems its salt form is very hygroscopic and that it doesn't mind throwing the hydrogen chloride out the window. Either way, after about an hour, it should be finished and the mixture has become green. That's at least better than yellow. Now that Lugduname should be here, hopefully in its hydrochloride salt, it can conveniently be precipitated with ether. So I set up a large flask and added in some ether. I then add in all of the reaction mixture and something precipitates. I wash out the flask with ether and also add more ether to make sure everything precipitates. I set this mixture in the freezer at -30°C to allow it all to settle to the bottom. It has settled as a green liquid, so I can first decant off most of the ether, and I then pipette all of the green liquid into a tiny flask. This liquid should contain Lugduname, but there is very likely some impurities and solvent. Either way, I can already snack on it before I attempt to purify it, since as I said before, it is quite sensitive and will end itself if you column it and then evaporate it down with heat. So I can take the tiniest amount of material in the tip of this pipette and put it on my tongue. Since I have been snacking on all of my products of my attempts these past months, I already know what it tastes like. Just as now, it first hits you with a weird flash of sourness. Maybe that's the hydrogen chloride. But then it slowly builds up and becomes sweeter and sweeter. It also stays in your mouth for a very long time, as even the tiniest trace can give you the feeling of sweetness. And you will also randomly find one molecule on your lips hours later. If you get a good amount of it, it also seems to activate receptors all the way in the back of the throat that I didn't even know I had. Also, every time I try this, and I don't know if it's between my ears, but it gives me more stomach acid and even acid reflux. As far as I am aware, your brain generally responds to the sweet taste in your mouth and increases stomach acid production as it anticipates food. Anyhow, does it taste like 300k times sugar? No. Is it very sweet? Yes. Which makes sense, since the 300k refers to a concentration in water compared to sugar, not the sweetness you perceive when you eat it directly. So now I will try to purify it and see afterward if I can put it in water and how it differs. For that, I will have to do column chromatography again, but this time I will just wet load the sample. So I dissolve it all in a small amount of dichloromethane and then set it aside for a second. I set up a column again and used 200 grams of silica gel and the same element as the first column, which is 5% methanol in DCM, and gradually I increased the concentration of methanol to elute the product faster. I packed the column and put a layer of sand on top. Unfortunately, this one decided to crack very quickly, because it is quite hot now and DCM can boil and form pockets that gets worse and worse. Ideally, I should also have left the eluent and silica gel sit for longer so that any exotherm from the mixing has passed. Either way, I will just continue. So I pipette all the solution on top of the sand and run it through like before. Since this eluent makes the column transparent, we can see the components move through the column, which makes it very easy to track. Even though it is cracking a lot, it looks like the components move through normally. When it's finished, I have collected a bunch of different fractions, but I am not sure which one contains Lugduname, so I evaporate them all down separately. It's a bit of an issue since it doesn't like the heat from the distillation, causing it to partially degrade. This fraction contains some yellow oil along with some red crab, and I pipette it into a small tube. I do the same with each fraction and afterward I am left with something in every fraction. As they became more concentrated, they started to become colored, perhaps from degradation. Anyhow, I sacrificed my tongue for the greater good, tasted all the fractions, and the sweetness is surprisingly, or unsurprisingly, in the most disgusting looking fraction. Now, I will do another direct taste test, and it's the same as before. Now let's just check if it will dissolve in some water and make it sweet. So I have filled this glass with regular tap water, and I add 2 small drops of the material into it. It dissolves easily, as at least the hydrochloride salt should be fairly soluble in water. So now it's time for a taste, and it's actually a lot better than I expected. It is very sweet for how little I put in. It's like I put a huge amount of sugar in, and it no longer has that initial sour hit when it's dissolved. However, it doesn't taste exactly the same as sugar. It is most similar to stevia without any bitter aftertaste. Initially, I wanted to produce a large amount so that many other people could try it as well, but unfortunately it is heat sensitive and distilling after the column kinda messes it up. So if you want to try it yourself, you can just follow this procedure and maybe even improve on it by not using heat or something. Either way, I will get it analyzed with NMR to see how pure it is, and I will post about that on the community page. So that was it, the sweetest compound known. Maybe one day I will unleash current day medcam on it and fluorinate the shit out of it so that it also gives you cancer. That was it, see ya.